So good morning, everyone. My name is Praful Lalchandani, and today I'm excited to take you all on a journey from myths to solutions in the world of AI data centers. Now, when it comes to networking for AI, there are more than a few myths that need to be debunked and a lot of self-serving arguments out there from vendors. So in this session today, we're going to help you demonstrate how we are debunking some of the biggest misconceptions out there and showing you how Juniper Networks is taking an evidence-based approach to demonstrate what truly matters in the context of networking for AI. So let me start with Juniper's missions for AI data centers. We know that GPUs are expensive. While GPUs are the currency for the AI revolution, building even a small cluster of just 8 to 16 nodes can lead to a capex investment of easily $5 to $10 million. Now, we believe that while networking is a smaller percentage of that overall capex investment, networking plays an outsized role in maximizing the return on investment on your GPU assets. As Mansoor mentioned, if GPUs are sitting idle, it's a sad situation. So our mission for AI data centers is to unlock the full potential for our customers' AI infrastructure, the AI projects, by A, delivering unparalleled network performance, 400 gig and 800 gig, B, ease of operations using Appstra, and 3, a lower total cost of ownership versus other proprietary technologies out there. Now, this is a level setting slide to show you what's the life cycle of building an AI application. Nothing new over here that Juniper is sharing. But the way it starts is first you gather data, you pre-process your data, you curate your data, eliminate biases, and that data is now fed into a training model, which is really a neural network or a machine learning model, which is learning to recognize patterns from the data that has been fed to it. And then the rubber hits the road when the model is then packaged into an application, deployed for inference, and it's now starting to make predictions based on new user inputs. The reason for level setting that is that Juniper has solutions for both training as well as inference clusters. Now, let's look at the requirements for network requirements more specifically for both of training as well as inference clusters, starting with training. Training can be foundational model training, which is really training a model from scratch. Example of this would be GPT-3, GPT-4, Llama 2, Llama 3, where you're taking an uninitialized model and training its weights and biases based on the data that has been fed to it. Foundational model training can require thousands and thousands of GPUs, probably the highest class of the GPU that is possibly out there, versus fine-tuning. Fine-tuning is really at the task of taking a pre-trained model and adapting it for a specific task. So this may be for a very specific use case in automotive or finance or whatever the use case might be. But the idea is you take a smaller, more specific data set and you train the model for a specific task. Now, fine-tuning requires much lower scale than the kind of scale you need for foundational model training. This could be 64 GPU, maybe thousands of GPUs, but not the tens and thousands of GPUs that are required for foundational model training. But whether it is foundational model training or fine-tuning, what we see is that the elements of the training cluster sort of remain the same. You have a GPU cluster, which is your set of coordinated GPUs. You have dedicated storage, which is high-performance storage. This is where your data sets that are being used to train the model are residing. This is where intermediate checkpoints, gradients, all of those things are in your dedicated storage. And then you have shared storage nodes where everything else, all your other artifacts, your logs, everything else is stored in shared storage. Now, for this session, the three critical things that we want to talk about is the network. There are three separate networks that participate in this AI training cluster. You have the backend GPU training network, which is GPUs talking to GPUs at very, very high speed. You have a backend dedicated storage network, which is GPUs talking to your backend dedicated storage. And then you have your front-end network, which is your connectivity to the outside world. It's where client requests come in. It could also be where your orchestration is residing, or it is almost always where the orchestration is residing. This could be Slurm, it could be Kubernetes, which is orchestrating jobs across your cluster. As Mansoor mentioned, the key thing in the key metric for training jobs is job completion time, which is how much time does it take to train a particular job with a specific data set with a target accuracy in mind.
Can you talk about job completion time a little bit within an AI context? Because I don't understand that. I haven't really seen job used for AI before. I mean, it's very common in HPC, but especially foundational, like a lot of training, these are not so much jobs as continuous feedback. It's not really feedback, that's the wrong term, but continuous feedback loops.
Yeah.
Not really jobs, unless you say a job lasts 2 months for a foundational model.
So inference is real time and it is continuous.
Yeah.
But before
Well, training is
a one-time.
continuous. It's
Well,
a one-time
training-
long job. I mean, unless I'm misunderstanding, which is totally
So
possible.
training is actually is not. Sometimes it can be continuous, but very often when we are deploying a training job model that is trained for inference, it has been trained with prior data in place. I'll talk about RAG where it's live data coming in for inferencing. But typically, any job like a BERT or a Llama 2 or Llama 3, you're training it with your data maybe over a period of a week, then deploying it. Now, obviously, you gather more data and you retrain it and then deploy it again. But essentially, it's not always continuous. You train it, then you deploy it for inference.
So that training of a week is what you're calling a
Job completion time.
Okay,
Yeah.
because an HPC job might be a few hours that you have to wait a week for,
Yeah.
but it's still, okay, thanks.
Praful, does Juniper and Appstra play any role in the backend network?
Absolutely, we do. Yeah, that's what we are. This session is about showing you how we play. Yeah.
Okay.
All right. So, so again, just to give you a little bit more appreciation for why the network is important for job completion time and the economics of job completion time, the reason for this is job training doesn't happen in one GPU. It's a cluster of GPUs that are coordinating to train that job over a period of hours and weeks. And this is an example of a data parallelism where you have a very large data set that is sliced into chunks, federated to the GPUs again over the data center fabric. And the GPUs there all do their individual computations. They're basically calculating the weights and biases, the gradients for the neural network. But before, and this is the critical piece, before the next set of data can be fed to the GPUs, all the GPUs need to merge their computations. That merge is when a burst of traffic hits the backend GPU network, and this is where network efficiency becomes critical. Because if there is any bottleneck, so let's say GPU 8 is not able to talk to GPU 10 effectively or at very high speed, all GPUs in the cluster are sitting idle. Not just GPU 8 and the GPU 10 which lost packets. Every GPU in the cluster is sitting idle, and that's again lost time that you don't want to happen in your infrastructure. Another example of this could be model parallelism, where even the layers of a neural network, the model is too big for all the layers of the neural network to fit into one GPU. So each layer or a set of layers is fed to different GPUs, and which leads to even more complex traffic patterns over your backend GPU networks. So hopefully that explains why eliminating those network bottlenecks is super critical in these infrastructure.
So that merging is done through the backend network and not through the front-end network?
So the GPU computations are definitely happening over the backend network. The front-end network is really just for job orchestration. There's not a whole lot of traffic happening in a front-end network. The backend network is, you're accessing data, that's your backend storage network. GPUs merging their computation is the backend GPU network.
Okay.
And Juniper does play a role, and I'm going to show you how. Yeah. So now we're moving on to inference. Now, inference can take on different cluster types. The simplest form is single node inferencing. Your job doesn't have, let's say, your model is not very big. It can fit into the memory of a single GPU. A single client request can be handled by a single GPU, sometimes even a CPU, if massive parallel processing is not necessary, right? A little bit more complex situation is multi-node inferencing, where your model like Llama 3 or GPT-4 may be too large to fit into the memory of a single GPU, in which case, again, even for inferencing, a cluster of GPUs across multiple server nodes is coming into the picture to handle the request even for a single client. In which case, you have a front-end network from where client requests are coming in, inference responses are going out, but you also have a backend GPU inference network. Now, this is not the most common situation. The most common situation is single node inferencing, but we have seen with our customers who are doing some things with Llama 3 and onwards, and larger size models, that they even have a backend GPU inference network. And the last situation is retrieval augmented generation, or RAG, which is becoming like a buzzword these days. The idea behind that is that, to the question before, you cannot be continuously training your model. but there is live data, and maybe you want the responsiveness of your model to be based on that live data that is available out there. So the idea behind RAG is that you supplement your inferencing with external or internal sources of data, and that is done using something called what is RAG. Now, we don't have time to go into RAG in a lot of detail, but I'll just talk about the network context. RAG generally has vector database involved. That vector database is stored in shared storage nodes and requires more high performance, low latency access into those vector databases. Now, like I said, training, the key metric is job completion time. With inference, the key metric is throughput and time to first token. Throughput is how many client requests can you handle per second. Time to first token is a measure of interactivity. So when you go to ChatGPT, you ask a question, what's the amount of time it takes for the first word to start getting typed? Is loosely reflected in time to first token. And again, network plays a key role in accelerating both throughput as well as time to first token. All right. So summarizing the network requirements, you have the front-end fabric. Front-end fabric we've typically seen is 100 gig to the host. It's always Ethernet. It is where you have your access to the outside world. So you have your leaf-spine fabric, but you also have your gateway, which is a connectivity to the outside world. You typically require multi-tenancy in that fabric because that's the fabric that is connected to almost everything. It's connected to your general purpose infrastructure. It is connected to your AI infrastructure. It is connected to your head-end servers where Slurm or Kubernetes is located. It's connected to pretty much everything. Plus, it's connected to the outside world. The backend GPU fabric is 400 gig. In the current generation of NVIDIA H100 servers, it's a 400 gig connectivity to each server. And you typically require lossless networking, and we'll touch upon lossless networking a little bit more detail, but we've heard Mansoor as well mention that you don't want to lose packets too extensively in that backend GPU fabric. And then backend storage, we typically see it as 200 gig today. Some of our customers are deploying at 400 gig, but again, you need low latency access to storage there as well. Now, for the rest of this session, we are going to focus on that backend GPU fabric and see what are the requirements and how Juniper is serving those requirements. Right? So there are three different technologies at play when you're building backend GPU fabrics. The first one is InfiniBand. I think everybody is familiar with InfiniBand, especially coming from the HPC world, where this was the gold standard. It kind of translated into AI training as well. So NVIDIA is the only vendor out there that is positioning switches based on InfiniBand fabrics. The second is an open Ethernet fabric solution, with the keyword being open. And there are multiple different vendors. This ecosystem is really big. There are many different vendors selling Ethernet switches, Juniper being one of them. And the last is a new class of products that is emerging, which is called scheduled fabric architectures. And they seem to have found a sweet spot, or at least they claim to have found a sweet spot with AI training. What scheduled fabric is also referred to as distributed disaggregated chassis. It's a modular chassis that is split into its components or disaggregated into its components. So the line card in a modular chassis becomes a leaf. Fabric in a modular chassis becomes a spine, and they somewhat act independently. So that's not where Juniper is, but there are other vendors out there that are pitching that architecture for AI training backend GPU clusters.
So where would Ultra Ethernet fit this?
Ultra Ethernet is an extension of Open Ethernet. So by the way, I just want to kind of maybe say, and then this question came in earlier as well, we believe the solutions exist, and we're going to show you some solutions that meet the demands of AI training networks today. Ultra Ethernet is only going to make it better. Juniper is completely participating in UEC, but it is only going to make it better. But we believe that we can meet the performance of InfiniBand today, and that's what we're going to show you.
Could you explain scheduled fabric again? I don't think I...
So scheduled fabric, if you know what a modular chassis is, you have line cards and you have fabrics. When traffic comes into the line card, the packet is chopped into cells and sprayed across the fabric. What a scheduled fabric architecture is trying to do is disaggregate that modular architecture into a leaf-spine fabric, but what's happening inside the leaf-spine fabric is still that cell-based or packet spraying architecture. So it's a modular chassis that is sort of disaggregated.
ATM will never die.
True. True. So all of these technologies, they're really trying to do only two things. And I know I'm oversimplifying this, but they're really trying to do only two things. One is congestion avoidance by better utilization of the available leaf spine capacity in your fabric. And different technologies do it differently. InfiniBand has a centralized guard called a subnet manager, which looks at all the flows coming in, all the paths to your fabric, and maps the flows to the paths. It's not a decentralized distributed architecture like Ethernet, but it's like got central control. Scheduled fabric, like I said, the way they try to do better load balancing or better utilization of available capacity is cell-based or packet spraying. Again, packet is chopped into cells by the ingress line card or the ingress leaf, goes over the fabric, the destination line card or destination leaf has to reassemble them into packets and send it on its way. Open Ethernet fabrics like from Juniper use more intelligent load balancing techniques, which I'm going to double click on. And the second thing that all fabrics are trying to do is congestion control. The whole objective of congestion control is to not lose any packets during your AI training run. InfiniBand and scheduled fabrics do it using a request grant mechanism. Not exactly the same, but I don't want to get into details of how InfiniBand works and scheduled fabric works. But the general principle of this is a sender, before sending a packet to a receiver, will send a request to the receiver. Receiver says, okay, I have the buffers to accept this packet. I'm going to send a grant back to the sender, and only then the sender sends the packet through the fabric. Open Ethernet solutions use techniques called DCQCN. Again, the middle column I'm going to explain a little bit more in detail, both because those are Juniper solutions, but different techniques used by different technologies. I said this was going to be a myth-busting session, so after that little bit of an academic setup out there, I'm going to jump straight into it. The first myth that we want to bust is Ethernet does not match InfiniBand's performance for AI training. Now, we being Juniper, I think you know what the answer is going to be, right? But we want to show you why and how. Now, we can write a lot of blogs and white papers out there explaining the theory of why Ethernet solutions work over InfiniBand, but you're not going to believe us. So as Mansoor said, we built out this AI innovation lab at Juniper because we wanted to run real training jobs, real inference jobs on a cluster of GPUs and accelerators and prove that our job completion times on this Ethernet network matches that of InfiniBand. So let me geek out a little bit and explain what this infrastructure actually looks like. So we built out a cluster. What you see in the middle over there is NVIDIA GPUs. So this is 64 A100 GPUs and 32 H100 GPUs. We have the dedicated storage. We have a Veka storage over here. It's a high performance storage used for training, used to store the data sets that are used for training the job, like I mentioned. We have our shared storage, which is used for anything else like logs, other artifacts, etc. It's also where the head-end servers are located. We are using Slurm for orchestration of our jobs in this case, but other customers in production could be using Kubernetes, OpenShift, so on and so forth. Now, talking about the various fabrics, like I said, the backend GPU fabric is the focus of this discussion. So I'm going to talk about it a little bit more. We have the A100 servers connected at 200 gig to the fabric. We have the H100 servers connected at 400 gig into the fabric. And these are essentially connected in what is referred to as a rail optimized design. Rail optimized design is something NVIDIA has as part of their SuperPod or SuperPod reference designs. What we have done is kind of mimic that design, except we have replaced InfiniBand switches with Ethernet switches. And the idea behind a rail optimized design is that GPU 1 from each server connects to leaf 1, GPU 2 connects to leaf 2, and GPU 8 from each. So by the way, each server has 8 GPUs. So GPU 8 from each server connects to leaf 8. And Juniper refers to this collection of 8 leaves as a stripe. And in this design over here, we have 2 stripes that are then interconnected by a spine layer. Now, the reason for this rail optimized design is to minimize the number of hops through your fabric. So what that does is that each server itself has an NV switch or a switch inside the fabric, inside the server itself. So all GPUs that communicate within the server don't need to come out to the fabric. They will just communicate within the high bandwidth NV switch in the server itself. All GPUs within the same stripe communicate only at the leaf layer. No traffic hits the spine. Or it's only when your GPUs need to talk across stripes, when you have a large enough cluster, is when the traffic actually hits the spine. So each stripe can support like up to 256 or 512 GPUs, depending on the size of your leaf in that design.
Can I have a question about these 5200? So for the backend, the leaf layer, 5200s at the backend, 5200s for the dedicated storage. These are like physically the same 5200s, or
no, physically different switches.
Physical different switches. Okay,
yeah.
Thank you.
Yeah. Yeah, and the 5200s are essentially a Tomahawk series of products, Broadcom Tomahawk series of products.
Thank you.
That's the backend GPU fabric. Then we have the backend storage fabric. Again, it's a leaf spine design. And then we have a front-end fabric, which is also another leaf spine design that is connecting to the shared storage nodes, is connecting to the Slurm. It's also connecting to the outside world for client requests to come in.
I mean, the challenge for something like this is it's orders of magnitude smaller than what larger language models are actually trained on.
So we have trained GPT-3, we have trained Llama 2 on this cluster, but with smaller data sets. Now the proof, I mean, we in our lab, we are not going to be able to build 1,000 GPUs, but our proof point is our customers. We have customers who are running clusters that are tens and thousands of GPUs. So yes, in the lab, we can only scale to a certain extent, but the proof point is our customers to a certain extent.
Are you gonna go through some like data and like how long did it take and like you will go through that? Okay, cool.
Yeah, right here.
Oh, okay.
So, I mean, that was the whole goal of the setup, right? Again, we said, we don't want to put theories out there. We want to put it in practice. So we ran ML Commons jobs. Now, ML Commons, for those who are not aware, is a body which produces standardized data sets, standardized, or as I should say, reference data sets with reference models. So all vendors can do an apples to apples comparison. So we ran BERT Large, we ran DLRM, we ran Llama 2, we ran GPT-3, we ran other things as well. But if you look at our job completion time for 64 A100 GPUs with BERT Large, we achieved 2.6 minutes of job completion time versus InfiniBand metrics posted out there, out there in ML Commons. We didn't test InfiniBand. These are standardized benchmarks. So we're measuring against what's posted in ML Commons, range from 2.5 to 3.3 minutes. Llama 2, if the number is catching your eye, why is Juniper at 7.9 minutes versus NVIDIA is at 5, or InfiniBand is at 5.1 minutes? The reason for that is that we have only 32 H100 GPUs, and the closest benchmark posted has 64 H100 GPUs, right? But we feel very good about this number. Generally, not perfectly linearly, but we expect job completion time to improve somewhat linearly with doubling of GPUs. So while we have half the number of GPUs, our job completion time is not double that of InfiniBand posted numbers out there. So we feel very, very good about these numbers. It's not just these. Customers have come to us during POCs. They have brought their own models. They said, we don't trust MLPerf to be reflective of our own production traffic. We're going to get our own models, run it in your lab, and see what happens. And they have come back with the same conclusions that they get similar comparisons, similar results to what they see with InfiniBand in their own labs.
So MLPerf and things of that nature, they're a lot dependent on the hardware configuration. It's not just the GPUs specifically, it's the CPU,
it's the storage,
cores, storage, and all this. Storage not as much for these sorts of activities because it's all direct storage.
Yeah.
But so you've matched the hardware configuration in the BERT Large, for instance, that.
When you say hardware, we match the GPUs.
So the CPUs and the cores and all that other stuff and the RAM and stuff like that needs to also be matched, right?
Yeah, I mean, in fact, even the software stack matters. So we can also matching the software stack as well.
Yeah.
Now we are thinking that any vendor who puts numbers out there is putting their best foot forward as well, right? Mm-hmm. So I think what matters the most obviously is the class of the GPU, whether it's the A100 or the H100 or how many GPUs you have. That makes the most difference. We've seen storage actually makes a difference if you tune it right or you don't tune it right. That can be the bottleneck. The nickel versions can matter sometimes. Those lot of things that matter. But again, because these are standardized benchmarks, it is coordinated to the extent it is possible. Yeah.
So are you submitting these benchmarks
yes.
to MLPerf? So
they already are
actually publicly available numbers.
Correct. Yeah, we are. Actually, coincidentally, today was the day it gets published.
Yeah.
So the answer to that question, the myth busting answer is false. we believe that Ethernet performs, and that raises the questions for our customers: is the cost and complexity of InfiniBand worth it? To my earlier point, it's not just us saying it. Our customers are saying it. Some of the largest cloud providers in the world are saying it. Meta has publicly stated that they are using both Rocky V2 and InfiniBand, and they get similar network performance using both technologies, right? Uh, NVIDIA in their last earning release, and I should say more specifically, Jensen in his last earnings release said we are all in on Ethernet. So I think the world is coming to the conclusion slowly that Ethernet can perform, and we are doing our part in proving that Ethernet can perform, and specifically Juniper's AI optimized Ethernet can perform as well.
So isn't it like also one of the benefits of InfiniBand over the Ethernet? Like you can run like loads of parallel trainings simultaneously.
And that's no different over here as well.
Oh, okay. So you've done that because when you were showing those numbers, that was sort of kind of like where you do like one training at the one time.
Yeah, all benchmark results on ML Commons are one job at a time.
Okay.
But it's not stopping. We can run, like you can carve out the cluster. We have Slurm running as an orchestrator. Very often in our lab, we have sliced this infrastructure for different experimentation purposes, and we are running different jobs at the same time. Sometimes inference, sometimes training, multiple training jobs over Ethernet. So we are doing it. Yeah. A lot of cloud providers are running on Ethernet as well. It's not just, and I should say specifically infrastructure as a service cloud providers are running over Ethernet. And for them, their customers could be doing something they don't even know what they're doing, and all at the same time. All right, we talked about performance. If you look at the economics, ACG Research did an independent study comparing the economics of InfiniBand over Ethernet over a 3-year time horizon, and they came to the conclusion that InfiniBand is 122%, and I should just be explicit, not 22%, 122% more expensive than Ethernet. The drivers were simple. I think we talked about them. InfiniBand is a vendor locked-in solution. It is more costly, and InfiniBand has been traditionally more operationally difficult to manage. With Appstra, as you will see in a few demos from following me, we made it really, really simple. Skill sets, toolkits for InfiniBand are hard to come by. They're not standard out there in industry. We all know how to manage Ethernet IP networks. Those skill sets are easily available. The toolkits are easily available, and that makes it operationally simple to manage Ethernet. Other benefits that are not even factored in this report is Ethernet is going to win out in the future, and Ethernet is GPU agnostic. While today the market is locked by NVIDIA, AMD is following right after, Intel is right there. The other accelerators like Sambanova and Cerebrus, all of those vendors we are actually currently working to build reference designs with. The market ecosystem will open up, and you want to bet on something that has better investment protection.
Praful, where does smart NICs and things of that nature fit into this? I mean,
let me try to cover it in the next myth busting, and I'll touch upon it a little bit. So the next myth that I want to bust is packet spraying is required to maximize performance in GPU backend networks. And a little bit of I'm going to go into theory again. Like I said, every technology needs to do two things. One is congestion avoidance and congestion control. So congestion avoidance is really the task of better utilization of available leaf spine capacity. Because the problem that exists in Ethernet networks is that even if you throw bandwidth at the problem, like 400 gig and 800 gig, you can still hit collisions. You can still hit congestion points because of the way static ECMP works. And so if you look at the picture on the right-hand side, multiple 400 gig flows coming in on a leaf, they could get mapped using static ECMP to the same leaf spine uplink, and you could hit collisions on the uplink. Similarly, you can have collisions on the downlink from the spine down to the leaf. And that problem is actually worse in AI training networks because you have large elephant flows. And versus general purpose networks, you would have many smaller flows. Here you have fewer larger flows, and that means less entropy in your network. So we are using a combination of technique called dynamic load balancing, global load balancing, packet spraying in conjunction with smart NICs to kind of alleviate those problems. One of those technologies that I want to talk about is dynamic load balancing, which is an alternative to static ECMP, where we are looking at the quality of a link in order to make a deterministic decision, to make a decision on where a packet or a flow goes. The way we do this is, for example, in the picture on the right-hand side, GPU 2 is trying to send traffic to GPU 6. 3 available paths. Static ECMP would have just picked one of the paths based on a random hash. Here we take a look at the quality of the link and realize that at that moment in time, when that packet arrives, the path to S2 is the best quality path, and I'm going to send traffic there. Now, you ask the question, where does NIC play a role over here? This is exactly where it plays a role. When you employ this in packet spraying mode, or I should say per packet mode, DLB is making a decision on the quality of a link on a per packet basis. So each packet could go in a different direction. Now, it gives you good entropy across your network, but what you need to do is, in conjunction with smart NICs, you need to be able to have a smart NIC that can handle that out of order packets and place it in the right place in memory. So that's where we have actually tested with ConnectX-6, ConnectX-7, Bluefield 3 NICs. We've tested the solution with all the NICs out there, and we'll continue to test it with other NICs as they emerge in the market. But that's the downside of packet spraying, that you need those smart NICs on the other end. So we have something called flowlet mode. A flowlet is essentially a burst in a flow. And as I said, in AI training jobs, you have a computation phase when the network is actually sitting idle, and then you have a merge phase where bursts hit the network. So what we do is we split those flows into flowlets. A flowlet is essentially a burst in a flow, and we make the DLB decision based on a flowlet, not on a per packet basis. And when we again put those things to the test, so again, this is the DLRM job training time. DLRM is a job that is running. The numbers you're seeing over here are job completion times. And we tested static ECMP, DLB flowlet, and per packet spraying. And what you'll see over here is that, and again, various columns are various load conditions. So the first column is there's zero background traffic. And the last column, there's 37.5% background traffic generated by Ixia RDMA traffic. And what you see is static ECMP, as I said, gives you the worst performance. And if in fact it degrades pretty badly once you have congestion in your network. DLB flowlet is very, very deterministic. Going from 0% congestion to 37.5% background congestion or background traffic, it gives you fairly deterministic job completion time for DLRM. Per packet spraying gives you the best results, but only marginally so. It's only 0.08% better than DLB flowlet. Now, another way to look at it is this. Now, this is like on the left-hand side, you see the static ECMP, and the various lines are utilization of the leaf spine links. So you can see that every link with static ECMP is utilizing those links at a different rate. At the lowest, it's about 150 gig. At the highest, it's about 350 gig. So you're not getting even utilization of your leaf spine capacity, which was the goal of congestion avoidance. But DLB flowlet gives you amazing, uniformity. So every link in the leaf spine fabric that is being measured out there has pretty much the same utilization over that entire training run. And like I said, that was the goal of congestion avoidance, and it's like very very well achieved with DLB flowlet. So again,
So Praful, you have a slide that shows what the packet spraying would look like on these links?
It almost indistinguishable from DLB flowlet.
Okay.
Yeah. So the conclusion that we're driving over here is, yes, it is theoretically true that packet spraying is the best results, but not practically so. Like I said, it's only 0.08% better than DLB flowlet. But it does require you to have more expensive NICs. So yes, our solutions from Juniper have the optionality to work NIC agnostic, or we have tested out solutions in conjunction with the smart NICs out there. But is the value that you get from packet spraying incremental value worth spending more on the NIC side? The other thing I will mention is that the scheduled fabric architectures I talked about, one of the core elements of scheduled fabric is packet spraying or cell-based spraying. So again, that leads to the question, is scheduled fabrics, the additional cost and complexity of scheduled fabric, is it worth it, given that we have shown you that DLB flowlet with standard Ethernet can give you almost the same performance as packet spraying? Okay. So the next one is actually the most popular question that we get from customers. So this one is 1:1 non-blocking performance is required to maximize performance in your infrastructure. So now let me explain what the question even means. It means that if you look at a given leaf, non-blocking means that your total downstream capacity of the host is equal to your upstream capacity to the spine. So for every 400 gig I have down, I have 400 gig up. 2:1 oversubscription would mean that I have 2x the capacity down to the server relative to the capacity I have to the spine. So for every 2 ports of 400 gig down to the host, I have only 1 port of 400 gig to the spine. So again, like I said, this is probably the most popular question we get from our customers. Should I build 1:1 non-blocking, or should I save some cost with 2:1 oversubscription because I have less optics, less number of spines, less number of cables, less complexity? Now, knowing that where my last two myths have gone, where do you guys stand on this? Who believes this is true? Raise show of hands. Who believes this is true? Nobody. Who believes it's false? Nobody.
Prove it, baby.
Prove it. All right. So far, everything has gone false, right? So here the results are right here. So what we saw is that we had I'm going to start with the one on the right-hand side because it's the most drastic. We had a customer come in. Again, customers are coming into us in our lab. They're running their models because they don't trust MLPerf. They're running their models. And they found that they had a 90% impact to job completion time when they went from 1:1 non-blocking to 2:1 oversubscription. They clearly walked out with the conclusion, we are going to build with 1:1 non-blocking. But when we put that to the test with other models, the other most extreme situation that we saw was with DLRM, where we saw only 1% degradation in job completion time. So this kind of leads us to the quick conclusion that yes, it is true that 1:2. I think in general, we would recommend customers to go with 1:1 non-blocking. The reason for that is most of our customers don't know what their researchers are going to be running, let alone today, 1 year down in the future. If you're a cloud customer, you have no idea what your customers are going to be running at all. Even if you're an internal IT shop, you may not have predictability into what your researchers, your data scientists, your various business units are going to be running. If you have no visibility into what your model characteristics are and they change on a periodic basis, Juniper validated designs will recommend that you go with a 1:1 non-blocking architecture. Simply it gives you the safest solution out there. If you really know what your model behaves and you have predictability into what it can, how it's going to be, what's going to be running over a duration of time, you can possibly try it out with 2:1 or higher oversubscription. But in general, we recommend 1:1 non-blocking. Even if you go with 2:1, you may want to think about whether the cost savings that you're getting is worth losing the optionality of maybe having to run different things in the future. But Juniper's AI Lab, if you're a customer, Juniper's AI Lab can definitely help you characterize your model for not just testing whether you want to do non-blocking or not, but with many other things as well. All right. The next one is lossless networking is always required in the backend GPU fabric. Even though over the past 30 minutes, I've said that losing packets is bad in AI training clusters. But the question over here is you really need 100% lossless networking 100% of the time in AI training fabrics, and how does it impact your job completion time? Now, we hear this a lot from our customers, networking people, researchers, data scientists, because there are some scars from the HPC world where losing a packet was really, really bad. And they've carried those scars into the AI world. But is losing a packet in the AI training realm as bad as it was in the HPC world? Let's look at that. So now again, a little bit of theory. Ethernet does congestion control differently from in the way InfiniBand does it. We use a combination of techniques collectively that are referred to as DCQCN or DC data center quantized congestion notification. This is a combination of explicit congestion notification and pause frames. Explicit congestion notification, the idea is switch sees congestion, it starts marking packets as having seen congestion, and eventually an alert goes to the source who slows down. Pause frames is a measure of last resort. We call it an insurance, where if a receiver starts getting his buffer utilization at around 80%, 90%, it basically tells the sender stop sending me packets until I clear these buffers and then send it after that. So collectively, this is referred to as DCQCN. But the question is, yes, we can deliver lossless with Ethernet, but is lossless 100% lossless the goal? So again, the same customer, we put their model to the test. Two scenarios. Scenario one, where we had ECN only, and as expected, you lose some packets. And in scenario two, we had both ECN and the insurance, which is pause frames, turned on. And as expected, we get lossless capability with scenario number two. But surprisingly, what this customer found was that, first of all, a lot of researchers and others people have said they think that a job will completely fail if you lose a packet. Job doesn't fail. There are some retransmissions that can happen. Maybe in the HPC world, there was some different behavior. But here, a job doesn't fail. But we also saw that they got better performance with scenario one, where you actually lost a few packets and actually got better performance than not losing any packets. And they actually got worse performance. And more explicitly, they got an 8% degradation in performance. So if that makes sense, we were actually surprised by the results ourselves. So after the customer left, we ran all our MLPerf models against the same scenario.
Sorry to jumping in.
Yeah.
On the previous slide. So
Yeah.
the packet loss, that's interesting. So like, do you have roughly an idea like what was that packet loss? Like, what is that like sort of like line, how far you can go in terms of the packet loss?
Yeah, so you cannot. I don't have the exact number right here with me, but you cannot like lose 20% packet loss.
Okay.
But here they basically what they did was they allowed their applications to breathe a little bit.
Right.
Otherwise, what happens with PFC is that you are throttling all flows in your entire fabric. Like you're telling them slow down when they might not need to. But here they saw that with by allowing their applications to breathe a little bit and maybe losing some packets and then retransmitting. And I know I need to quantify some for you, but you cannot lose a whole lot of packets. But you can allow
say like up to 5%.
Maybe possibly.
Yeah. Okay.
It depends on the model, but
Depends on the model. Oh, okay.
And then
Depends on the model, the size of the cluster.
So which models are like less sort of like touchy about packet loss and?
So this was the most touchy. Of all the ones that we tested, like when we put DLRM to the test against the same scenarios, we saw that this one couldn't handle packet loss. We saw a 22. We saw the opposite results of the customer model, where this one couldn't handle packet loss. We saw 22% degradation. We realized that for this model, we always had to have PFC turned on to have that lossless behavior in order to get the best results for this one. So, leading into the conclusions is that the one conclusion is that yes, from the HPC world, there is some battle scars. Don't always translate the same way into an AI training world. 100% lossless does not always yield the best result. Job definitely doesn't fail with a few packet loss. And the theory behind this is that sometimes when you have a high bandwidth 400 gig, 800 gig network, losing a few packets and retransmitting is probably better than having everybody back off in the whole infrastructure, right? That's the theory behind the empirical evidence that we're kind of seeing over here.
So how do you work with the AI engineers then to understand which side their model fits on, the one that's very sensitive to the packet loss,
so we can
or
run
the
this
one
test
that's
in our
sensitive to being throttled?
So we have customers who actually do bring their models to our lab and to test it out. So if
there's no standard that they can measure their model against theoretically to know that, you actually have to practice.
So one of the exercises that Juniper is running right now is we are trying to characterize the different type of models and come up with some standard solutions. I don't think we're there yet, even not just at Juniper, but even as an industry, to be able to say that your model is type A, and this is what you need, and model is type B, and this is what you need. But that's exactly the goal of our experimentation in our lab, to continue to get to that point as an industry as a whole.
There's no correlation to data parallelism versus model parallelism versus no parallelism in this discussion?
There could be. I don't think we have done enough range of different models to arrive at some conclusion out
based
there.
on that.
Yeah, but I think
You don't know?
So I'll be humble. This last 4 months that we built this lab, we've learned a lot. I think there's a lot more to learn. We're going to be experimenting along with customers. And Ali, that was our next slide.
So, real quick before you go on, I think, did I hear you correctly that you said if somebody has challenges, they should bring their model to your lab?
They can. They don't have to.
They don't have
Yeah.
to. Is there a way you can leverage the Appstra and the telemetry and get access to the data and look at what's going on locally to do?
Answer is yes. Yes.
Okay.
Yeah.
You have a demo to answer.
That's
Okay, thank you.
So can I just clarify a thing about that packet loss? So like, where was that bottleneck? Was that the demarcation line was the networking card on a server? That was the bottleneck. That's where you've seen the packet
switches were losing packets.
And then did you compare kind of where the loss, if there was a difference in performance depending on where the loss was happening, whether that was over to the supplemental storage or whether that was at the NIC or whether that was at the switch?
No, this loss was, I mean, more explicitly in this particular case, the loss was happening on the spine. Yeah.
loss? So you were like filling up the buffer.
Buffer on the spine.
Oh,
yeah.
okay. So there was like overflow.
Correct. Yeah, again, we didn't put the insurance of pause frames in scenario number one. So you do expect to see some packet loss in that environment. Yeah.
Interesting. Okay.
Yeah, we had a feeling that would be the most interesting, controversial one. So anyway, our lab is open to customers. We will continue to experiment. I don't think we're the end of our journey, but this design lab is, been great at learning a lot. Those best practices and learnings feed into our AI JVDs that Mansoor talked about. These are Juniper validated designs. One of the artifacts of the Juniper validated designs are design docs that are published on .NET, accessible to everybody to see. But the other artifact of the JVD is Terraform configs. And what customers can do is on their own Terraform instance, they can download or import these Terraform configs and then deploy these Terraform configs into AI fabrics into Appstra. So whether you need a 64-slide GPU cluster or you need a 4,000 size GPU cluster, all the best practices feed in via this overall linkage into Appstra so that you get our learnings from the lab into designs that you can deploy for AI clusters.
So that's not just a PDF, that's the actual configs that you can import directly into Appstra? That's very cool.
We publish configs, we publish Terraform templates. Terraform templates can then be loaded into Appstra. And that's the first demo that we're going to show you. So we're going to lean forward on operations for the next 3 demos. They're all Appstra-centric operations. Nick and Raj are going to talk about exactly that. How do we take those Terraform templates and load them into Appstra so that when you design your infrastructure, you already have your best practices loaded. Jay Wilson is going to talk about day 2 operations. How do I visualize congestion? How do I react to it? And then, because one size may not fit all, Vikram and Raj are going to talk about how you can use Appstra again to fine-tune your AI data centers to get the maximum performance of your AI. And look at that. Somebody snuck in a bonus Mythbuster just for you guys because we love you guys. We need more acronyms and terms in the AI world. Now, I'm going to leave that answer to you. It really depends on you. Personally, I lost my balance 10 acronyms ago. But our NEC presenter, Nick Davey, he calls himself Smart Nick Davey. He is super, super smart. And he says that he can handle 4 more.